Ladies and gentlemen, welcome to the March meeting of the Royal Astronomical Society of Canada, a very long name to mean Astronomy Club. Are there any people here who haven't paid their membership dues and aren't a member? You're welcome. We're very happy that members of the public show up. We don't care about the membership dues for this meeting. Tonight we have an observation-packed meeting. Anybody get to do any observing this February? Just curious. Anybody get to observe, say, more than 5 nights? Well, we can make up for it tonight because we have, I think, something like 13 different people presenting observations. So to start things off, Brian McCullough is going to talk about what we can observe in the next month, followed by Richard McDonald to give us the morning science content. Brian?
All right, here we go. A couple of things coming up. Of course, this time of the year, it's a very good time. Is the microphone on? Yeah. Very good time for observing what's known as the zodiacal light. So this is when you see the plane of the solar system, the ecliptic is tipped up much more toward the vertical this time of year. And what we can do is we can see dust reflecting sunlight off it. So you can see this cone of light in the west shortly after sunset. Comet Lulin in Gemini. And if you go to heavens-above.com for details. Don't go to just heavensabove.com because you'll end up in a place where I know you don't want to be. I found that out the hard way with my Algonquin College students in Pembroke. I said, oh, just Google in there heavensabove.com, and they were pulling up. Well, it was pictures of heavenly bodies, but they weren't astronomical. Okay. Okay. Asteroid Ceres. It's the first asteroid that was discovered. It's the largest one in the solar system. We'll be talking about that more in just a. I think. I can't even remember what slides I have. Do we have a picture of it?
Roll with the punches.
Roll with the punches. All right. So it's at the asteroid right now is passing through Leo Minor, and back into Leo, and it's at only 1.5 astronomical units. So which is 1.5 times the distance of the Earth to the Sun. So that's 150, 225. Is that what it is? Do the math. 150 plus 75, 225 million kilometers. That's the closest it's been since 1857, and it won't be this close again until, well, I'm not waiting up for it. Okay, on St. Patrick's Day, the night of St. Patrick's evening, if you haven't been into the green beer too much, there's a nice Moon and Antares conjunction, although it may look even better after the green beer. So you can watch, and if you're looking at things at a fairly close-up view, you'll see the Moon pulling away from the star. Spring equinox on the 20th, new moon on the 26th, and we've got an interesting here on the March 27th, 28th. Titan's shadow. Titan is, of course, is the largest moon of Saturn, and Titan's shadow will be cast onto the ball of the planet. So that would be observable through a telescope. I think we have a little clip of that as well. Let's see what else is in this bundle. We'll do it this way. If this were Saturn, you would see the shadow of Titan, actually probably coming this way, and it would pass right across the face of the planet. Was that a reasonable simulation? All right, so you can see there's Titan itself, but the shadow precedes it. Are you going to be able to reloop that? There it goes. Oh, the shadow's trailing it. All right, you can see how close to the horizontal the ring is right now. It's just, 2 degrees, two and a bit degrees off the horizontal.
So we're actually looking at the shadow side of the ring right now, at that time?
I don't know.
No, I think we're looking at the sunlit side.
I think, okay, Till is thinking the sunlit side. Good question. Okay, let's go on to the... All right, if you're still looking for Comet Lulin, all right, there's still some opportunity to see it, although it's starting to get somewhat fainter. But it's been traveling across. I mean, I saw it in Virgo down here. We'll see one of my sketches in a bit. Saw it down in Virgo this way about a month ago, and it's been traveling right across, almost following the path of the ecliptic. This is the path of the sun and the planets through the sky. So Lulin by tonight is somewhere right around in this area right here, just reaching this leg of Gemini. Okay, about a couple of days ago, it was just passing right near the beehive cluster in Cancer. All right, let's go to the next one, please. And I wonder why I have this one here. Oh, yes. All right. So if you're looking for Saturn, here's the constellation asterism of Leo, the lion, with the bright star Denebola down here, the main star, the alpha star Regulus, right here at the base. And you can see Saturn just down below here. So it looks like if you're looking for Leo and you don't recognize the shape right off the bat, that's why you're getting an interloper, as it is. All right. Just up here, this star right here is number 54 Leonis, the 54 star in Leo, and this is Leo Minor here. So this is why I say that this series, the asteroid, has been passing through from Leo into Leo Minor. It'll be going back into Leo in a very short while. So right now, it's just a couple degrees off from the 54 star. And if you go online, you can find finder charts for that, and it's relatively easy to do. I looked at it in binoculars, found it in binoculars, but I also observed it through my telescope. If we go to the next one, please, Chris. Is that it?
That's it.
Okay, so the rest will be in the observations. All right. Okay, thank you.
Thank you very much, Brian. Yes, Brian will be doing an encore later on. In fact, several encores. In fact, get used to seeing Brian tonight.
I'm sick of myself already.
Astronomy is much more fun when we know about a little bit of the science behind it. And tonight, to offer us the real science content, I like to insert in every meeting, is Richard McDonald to explain the most obvious secondary effect of gravitation, tidal forces.
Thanks, Attila. I have a bit of a cold tonight, so if I croak at you, I apologize for that. And don't push the button while you're walking away. That just throws things all off. There we are. Anybody know where those photos are? Bay of Fundy, yes. So that's what I knew about tides until very recently. And this is why I thought I'd put this talk together, because astronomy is filled with all of these discussions about tidal forces. We're hearing people throw this term around, Simon in particular, so smart it frightens me, throws out the word, oh, tidal force this, tidal force that, and I kept thinking Bay of Fundy, okay, beaches, can't use the beach twice a day. What on earth does that have to do with all of these astronomical phenomena? I didn't get the connection. So I did some research, and I'm going to share with you a very layman's view of what exactly is a tidal force anyway, and then what are some of the effects that it has around the solar system and nearby. So let's start with what are tidal forces? Now, like good scientists, we'll start with observations. So what is it that we've noted? I'm not doing that. Is the automatic time advance set by any chance?
Put it on.
No, I didn't. So, okay, well, that's all right. I'll just try to talk at the same rate the slides are moving. So what have we noted? Well, ocean tides, we mentioned that. We've noted the moon always faces the Earth, and we've heard people use the word tides to explain that. We'll come back to that. And we've heard people like Simon associate tides with a bunch of other phenomena, like moons being warm and comets breaking up and all sorts of cool things like that. So what's going on? Trying to keep up with this automatic timing is going to be just a delightful extra challenge here tonight. So what's going on? Well, we'll start with the prerequisites. To experience tidal forces, you need two or more objects. We're just going to use two in our examples tonight. They need to be similar sizes, a moon and a planet, two planets, two moons, not a planet and a grapefruit. Okay, similar sizes. And they need to be interacting gravitationally. Most common would be, one would be orbiting the other, or maybe they're passing in the night, but the gravitational attraction between the two of them is causing their paths to bend. So under those circumstances, we can experience tidal forces. So let's look at what's going on. We talked about gravitational interaction. What's going on there? Now, warning, there's a formula on the next page. So the faint-hearted, you might want to shield your eyes. Oh my God, two formulas. So now, you don't have to read or understand the formulas. That is not the point. Just aren't they beautiful? Newton gave us this formula for the gravitational attraction between two objects. I think that's very beautiful and elegant. And all I want you to notice is that the formula depends on the mass of the two objects. There they are, mass 1, mass 2, and the distance between them. And of course, r stands for distance. And the reason he uses r is because he wanted to remind us that it's the center to center distance. So the r is actually for radius, so center to center distance. Newton and Kepler, this is Newton's rewrite, also gave us this other very elegant formula. This is for the position of an object that's orbiting another object, or the speed at which it orbits if you already know its position. Again, mass of the two objects, distance between them, speed of the orbit. Now the reason I put these formulas up is I want to point out that in neither of these formulas is there any parameter for the size of the objects. The only thing that matters is their mass and the distance between their centers. So all of the gravitational interaction formulas that we have ignore the size of the object. We always treat center to center, and there automatically the centers have shown up. So if these objects are in orbit, for example, and it's stable, that means we've reached a balance where the force of motion, the centrifugal force, to give the physicists a headache, because they like to remind me there's no such thing, pushing that way, the gravitational force pulling this way are equal, and that's why the orbit is stable. And it's center to center that matters. So in the sense that, no, don't do that. In the sense that this is a stable system, you can think of the force there and the force there as zero. If it was greater, the objects would be flying closer together. If it was smaller, they'd be flying apart. So those center-to-center forces are very important. Which is interesting because, of course, the objects aren't points. They actually have a slight... Now, what are you doing over there? You're trying to stop the automatic advancing. Now they're backing up. You did. Wonderful. Because the objects aren't points. They have a width, which means that all the points on the objects are not the same distance apart. So they're not all experiencing the same gravitational force. These red dots here are closer together than the centers. So if you think back to that Newton formula, they must be experiencing a stronger pull of gravity. The yellow dots are farther apart than the centers. They must be experiencing a weaker pull of gravity. And relative to the center, this is feeling pulled together. Relative to the center, this is feeling less force, so in a sense, it's feeling pushed apart. That's the aha moment. You have to study this long enough to say, okay, if I set zero at the center, those dots there are feeling pushed apart. They're feeling less force than is felt at the center. There's a negative value there. And one night you'll wake up and, aha, I get that. And then all the rest of this works. If you carry that analysis on and you draw dots all over these objects and figure out what the forces are, you end up with this lovely diagram here. This is out of a 100-year-old classical mechanics textbook. So these are not new ideas. And what the author pointed out is, if this is a moon and it's orbiting a planet, the planet's over there somewhere, the too distant attracting mass, then you end up with these forces acting on the moon that looks sort of like this. The side closest to the planet is being pulled towards the planet. The side farther from the planet is being pushed away, because if you like to think of it this way, the centrifugal force of the orbit is greater than the gravitational in the center, so it's being pushed away. And if you do the math all over the object, you'll find these sides are actually being pulled inwards. So there's a squishing force going on here. It's being pulled apart this way and squished together from the top and the bottom. There's a scientific term for it, but I love the phrase squishing force, and I'm proposing that we use that going forward. And if you calculate the squishing force, you get this lovely, elegant formula, last formula in the presentation. Again, so the squishing force on a moon is a function of the mass of the two bodies, the moon and the planet, the size of the moon, and the distance between them. And notice the cube in the denominator there, the cube of the distance. So when you have a cube in a denominator, you're looking at something that falls off very rapidly with distance. That's why tidal forces are insignificant for objects that are any significant distance apart. They have to be really close together. And we're going to come back and see that effect in a moment. So let's look around some familiar objects and see what that squishing force is. If you just run that formula, that's a simple formula. You can do this in Excel, so I did. And here are some common objects that we're familiar with. Now, let's not worry about what the actual numbers are, because I have no idea how to internalize 10 to the 18th newtons. I have a feeling that's a lot of force. But you notice they're all 10 to the 18th newtons, so we can ignore that and look at these numbers here. So the moon is feeling some squishing force from the tide of the Earth, 1.8 times some huge number. The Earth is feeling a squishing force from the moon, 6.6 times some huge number. It's about 5 times as much. Well, the distance between them is obviously the same. The relative masses are obviously the same. Why the difference? Remember that the size of the object whose squish you're measuring was a factor. The Earth is bigger, so it's feeling more tidal force. The distance between the far edge and the near edge is greater with the Earth. So it feels more tidal squish from the moon than the moon feels from the Earth. The Earth also feels a tidal force from the sun. The sun is really big and really massive, but the force is smaller than it feels from the moon, and why is that? And the answer is the sun is a lot farther away. And remember that cube in the denominator. Okay? Distance is enormously important here. So the most important tidal influence in our neighborhood is the moon, even though it's not very large. So that's what that stuff says. So it's a squishing force caused by the difference in gravity on the near edges and the far edges of two objects that are interacting. Let's look at some of the effects that we see around the solar system. Well, the most obvious one is tides, duh. So let's look at ocean tides. Remember that diagram? There's a force there squishing in. So if you think of the effect the moon is having on the Earth is kind of squished. Now, is that actually squished? I can't tell from over here. Yes, it is. Okay. From over here, actually, it looks perfectly spherical from here. Now, obviously, that's exaggerated. The squish is only a few meters in reality, but the squish is real. So there's the moon. It's squishing the Earth. The Earth is slightly elongated. We call that the tidal bulge, but the Earth is rotating. So as the bulge rotates over or under the water, that's a high tide. The water bulges out as the bulge rotates under the water. As the bulge moves on, or rather the Earth moves on, then the high point moves somewhere else. As the bulge moves over land, no water is being raised. The land is being raised. It's been measured. The land actually raises up about 30 centimeters, according to the tidal force, as the bulge moves over the land. And that's continuing. And remember, the bulge is on both sides. That's why there's two tides a day, one on the near side to the moon, one on the far side to the moon. That always bothered me. I always thought the tide was the gravity of the moon pulling on the water. But how would that explain the high tide on the other side of the Earth? Right? That always bothered me. And it's the concept of the bulge. It's the difference in the gravity that is causing that. So that's what tides are all about. The other effect that we've heard blamed on the tides, but frankly I didn't understand until I got out my geometry set and worked it through, was the idea that we always see the same face of the moon. Now, why is that? Well, first of all, we often incorrectly say, well, it's because the moon's not rotating. Certainly it's rotating. The reason why we always see the same face of the moon is it's rotating at exactly the same speed at which it orbits around the Earth. So it rotates once every 27.8 days, or whatever that number is, same speed that it orbits. So it's always keeping the same face pointed towards us. Why is that? It's a tidal effect, and we'll walk through why that is now. Now, what caused that to happen to the moon happened in the distant past. But it's happening to the Earth right now. So I thought I'd actually walk through the Earth as an example and show you what's going to cause the Earth to synchronize its rotation with its orbit around the moon in only about 10 billion years. And then we'll go back and see, all we have to do is say, see, that already happened to the moon. So here's what's happening. We have the moon orbiting the Earth. Remember, there's a tidal bulge. Okay? And the tidal bulge wants to be facing the moon for reasons we've already gone over. But the Earth is rotating. And it turns out the Earth is rotating faster than the bulge can move through the Earth. It takes some time to move that bulge through the solid mass and the inertia of the water. So that isn't really what the diagram looks like. That is. Okay? The bulge is leading the line between the Earth and the moon somewhat. And the bulge is constantly going this way. The Earth is rotating this way. So the bulge is not lined up with the moon because the Earth is rotating a little too fast. That, of course, now is a target. This is something the gravity of the moon can act on. So the gravity of the moon is pulling back on the bulge. And it's actually slowing the rotation of the Earth. And we've measured that. It is slowing the rotation of the Earth by a few milliseconds every year, and that's why we have leap seconds, by the way. So the Earth is gradually slowing its rotation, and the day will come when the speed of the rotation of the Earth is exactly right so that the bulge is pointed permanently at the moon, and then this effect will stop. If the Earth was rotating too slowly, the bulge would be pulled forward by the moon, and it would be gradually speeding up until it lined up perfectly, and then this effect would stop. So that's going on right now. That happened long ago for the moon. When's it going to happen for the Earth? I wasn't able to get exact numbers. In something like 6 to 10 billion years was the best numbers I could find. The Earth will synchronize perfectly with the moon. And then if you were sitting on the moon, you'd always see the same face of the Earth. But it's going to be interrupted before that happens, because in about 4.5 billion years, our sun is going to swell into a supergiant and burn the Earth to a crisp. So we won't actually see this happen to the Earth, okay? But the theory is sound. Now, this happened to the moon long ago. Okay, the moon is much lighter, much smaller than the Earth. It was easier for the gravity of the Earth to act upon it. So the situation we have, again, that bulge is exaggerated, but the situation we have is the bulge on the moon is pointed directly at the Earth. If the moon were rotating any faster, the Earth would be pulling back on the bulge and slowing it down. If the moon were rotating any slower, the Earth would be pulling on the bulge and speeding it up. So it's reached a state of equilibrium, so we always see the same face of the moon. This is called a synchronous orbit or tidal locking. It's not a coincidence. Now, should it be easy to test this too? If this isn't a coincidence, you'd expect, well, maybe we'd see it elsewhere. So let's be good scientists and look around. This is a testable theory. Do we see it anywhere else? And the answer is, oh yeah. It turns out all large moons in the solar system are tidally locked to their planets, every single one of them. In fact, in Wikipedia, there are 34 objects listed in the solar system that are tidally locked to their planets, all kinds of moons, and even the planet Mercury is tidally locked to the sun. Now, Mercury is not a one-to-one lock. It's not always facing the same side to the sun. We thought it was for many years, and then we got better resolution radar telemetry, and we learned it's not. It is in a 3-to-2 lock, I think, where every 3 times around the sun, it rotates twice. I may have that backwards. It may be 2 to 3. But the message there is synchronous orbits other than one-to-one are possible. It can still be stable in an arrangement where, say, it turns twice for every once around the moon. Something like that is happening to Mercury. So that's a pretty good test of this theory, is that it's happening everywhere we look, where we would expect it to be happening, which I find fascinating. But I'm a geek. So let's look around. What other kinds of effects do we see near planets? My favorite one is this one. There's this neat effect called the Roche limit. And this is named after an astronomer, Edouard Roche. It's about a 150-year-old theory. And what he did was point out that if you take a planet and a moon, the gravity of the moon is holding the moon together. It's pulling itself in together. So he used the word cohesion. The gravity is a cohesive force. It's holding the moon together. But there's also this tidal force that we've talked about that wants to pull the moon apart. And the tidal force is a function of the distance. So there must be a distance, he said, where the cohesive force equals the tidal force. And if you got inside that distance, the tidal force would win and it would pull the moon apart. And as long as you're outside that distance, gravity wins and the moon gets to stick together. And he calculated that distance, and it turns out to be complex. It depends on what the planet and the moon are made out of and some other things. But a good rule of thumb that works is it's usually about 2.5 times the radius of the planet. So inside that distance, you would not expect to find moons because they'd be torn apart by the tidal forces. Or if there was stuff there, it would never form into a moon because the tidal forces wouldn't allow that to happen. And you'd expect to find moons outside their planet's Roche limits. I think that's kind of interesting. This is testable too. So do we see this? Sure we do. Every large moon in the solar system is orbiting outside its planet's Roche limit. And every ring system in the solar system, and there are 4, right? Every ring system in the solar system is inside its planet's Roche limit. So this is really strong support for this theory, and the rings are either a moon that got inside the Roche limit and broke up, or crud that was inside the Roche limit and was never able to form into a moon. This theory has no opinion on which of those it is. But that's really good support for the theory, and I find that very elegant. Now, this is very static. This is about where the moon's formed. What about if something is already whole and cohesive and healthy and it strays inside the Roche limit of a planet? What would happen? Well, we have an example of that. Hello? There we are. Anybody know what that is? Yeah, Shoemaker. Oh, look at the words. Shoemaker-Levy 9, a comet that was detected in 92? 4, thank you. That when it was detected, it had already happened. It had passed inside Jupiter's Roche limit. And there's what happened to it. It was ripped apart by the tidal forces of Jupiter, and by the time we noticed it, it was a string of things spread out over a long distance, and we got to watch those crash into the surface of Jupiter. It was very spectacular. So this is really good support for this theory, and the clear message here is being inside the Roche limit of a planet is a bad place to be. Tidal forces are significant there, and things inside the Roche limit won't be happy. So, which makes you think, wait a minute, isn't the International Space Station inside the Earth's Roche limit? Sure it is. It's well inside. For that matter, aren't I inside the Earth's Roche limit? And I'm not being torn apart by the tidal forces, so what's going on? And we have to remember that the Roche limit only applies to objects that are being held together by gravity. They have to be big, they have to be held together by gravity. And the easy way to tell if something is being held together by gravity is it's a sphere. If it's not a sphere, it's probably not being held together by gravity. I'm not being held together by gravity, even though I'm becoming spherical. I'm held together by electrochemical forces, molecules and things like that. Space station is held together by rivets or glue or something like that, not gravity. So this is not a contradiction to the Roche limit. One paper I read had a really good example. They said gravity is much, much, much weaker than the electrochemical bonds that hold us together. It's that much weaker. That's an incomprehensible number, 10 to the 36th. What the paper said is, if gravity was the same force as the electrochemical forces, when the Apollo lander returned from the moon, it would have pulled the moon with it. Okay. And, well, that didn't happen. So there's good support that these forces are quite different. So that's the Roche limit. I find it interesting. One last force in the local solar system that we'll talk about, and that will be tidal heating. Now, this one is a little more complicated, but we hear it being mentioned all the time. And a wonderful example is Jupiter's moon Io. When we were talking about the synchronous orbit of the moon, we talked about the tidal bulge moving through the Earth and that it could only do that at a certain speed. So what we need to heat a body is we need a bulge that is still moving. So our moon, the bulge isn't moving anymore, it's synchronized. The bulge is pointing straight at the Earth. So we need an object where that's not happening. And the most common source of those objects is places that are not in one-to-one synchronous ratios, like Io or Mercury. Io is synchronously locked to Jupiter, but it's also synchronously locked to the other Galilean satellites, Europa, Callisto, and Ganymede. And so it's actually oscillating back and forth in a fairly complicated way, which means the bulge is constantly moving through the planet. So if you've ever taken a blob of silly putty and squished it multiple times in different directions, you know what happens. The motion of the bulge through the planet heats it through friction. And that's what's happened with Io. It's so bulged and so heated by friction that the interior is molten. And in fact, it's the most volcanic object in the solar system. Those are volcanoes all over its surface there. And it's tidal heating, the internal motion of the bulge through its synchronous relationship with the other moons and Jupiter that is causing that. Now, would we expect to see that anywhere else? Sure. We'd expect to see that anywhere where there are moons close to large planets that are in some kind of synchronous relationship with other moons. You look around, and we do. All of the Galilean satellites, the four listed there, and Titan, orbiting Saturn, are all in this kind of a relationship. And tidal heating is contributing to the internal heat of all of them to at least some extent. In some of them, there are other factors as well, but they're all being affected by tidal heating. So I find that quite fascinating, and I can imagine what it would be like standing on the surface of something like that, where the interior is warmer than the space around it. And the effect is nothing but the gravity of the nearby planet and moons. It's a fascinating thing to think about. So that ends our tour of tidal forces in the solar system. I had more that I was going to put in, but to keep things short, I'm going to stop with just one more example. And that's to say there's tidal effects elsewhere. If we go back to what our prerequisites were, we said we needed two or more objects, and they need to be about the same size, and they need to be fairly close together. So we see that on all kinds of places, and one example would be interacting galaxies. Interacting galaxies are about the same size, and relative to their sizes, they're fairly close together. And when galaxies pass one another in the night, you get effects like this. They feel tidal forces from one another. They feel a stretch and a squish. And they're not very solid, so the way they react to the tidal forces is you get this crud streaming out in the direction of the tidal forces. And so astronomers call that a tidal tail. And that's why. It's precisely the same force we've just been discussing. As the galaxies passed in the night, the tidal stretch drew material out and left it lying in the wake of the interaction. So you see this force all over the place. Anything big enough for gravity to be significant experiences these things. I tried to find some papers on the concept of the Roche limit of a galaxy. It would have one, to see if there were any effects there that you could look for. And I haven't found anything, but I'm going to keep looking because I have a feeling there's some amusing stories to be told there and probably some spectacular pictures. So that's where we're going to stop, and I'm just going to give you a two-part conclusion. Here's the takeaway. So, tidal force is a differential force. That's the critical thing to remember. Tidal force isn't about the gravity between two objects. It's about the difference in the gravity at different points on two objects. The near sides and the far sides are experiencing different amounts of gravity. And that difference is the force that causes all of these effects. And the second point is that we see the effects all over the place. Think of it as a squish and a stretch. And you can think of all the places that this is turning up in our lives. Tides on the Earth, the easy one. Synchronous orbits, that's the bulge being pulled on by gravity. Destruction and mayhem as things get too close to planets. By the way, that's going to happen to the moon Triton in about 400 million years. It's orbiting the wrong way around Saturn, so it's going to get too close to Saturn, fall inside the Roche limit, boom, another ring system. No, Neptune, boom, another ring system. I'm going to wait for that one. Tidal heating, so you see this all over the place. So now when I hear the experts talking about tidal forces, I'm going to have a little better idea what they're talking about, and I hope it helps you too. So.
Excellent. Thank you very much. Richard, will we be available after the meeting to answer questions?
Sure.
Okay. By the way, there is a dramatic demonstration that shows the dependency of size on tidal forces, and it's a bit depressing. What it shows is that this bulge cannot be blamed on the mass of the moon. This is actually a mashed potato effect, not a mass effect. Right. How many people, when they go observing, just go outside the telescope and look at anything they feel like? And how many people sit down in advance and carefully plan their observing session? So who are the chaotic observers? Who are the organized observers? Okay, the organized observers are in the minority, so perhaps the chaotic ones need help. Joe Silverman is here to show us how to prepare an observing session with star catalog. I myself, am too ditzy to handle this kind of level of organization. Mike, or rather, Joe?
Okay, thanks. Start right away. Okay, this is a picture by Guy Ottawa, and sometimes when I'm at Nirvana, I just sit in a beach chair and I look up at the sky. And within a twink of an eye, I could go back dozens of centuries and sort of feel I'm looking at the sky as people then did. But due to the success of the scientific method, my perception of the universe is very, very different. Also, behind me, I have a telescope, I have a table, chair, and on that table, I have a star chart and a catalog of DSOs. Okay. Okay, I have a catalog of DSOs. And although you look up and you get this powerful G. Willikers experience, there's also, I like to intellectualize the experience as well, and I find that also very rewarding. And to do that, I actually need that star catalog and my telescope. And so what this talk will be about a bit later on is getting to sort of benefit from that experience by using a star catalog, and also understanding what the star catalog has in it, because it has classifications of various DSOs and other information that is pertinent to sort of making your experience very rewarding. Do I have to? It's not working. Okay. I went. Okay, now the idea here is this is the galaxy of the Milky Way. It's a spiral barrel galaxy, and we're 2/3 of the way away from the center of the galaxy. In the summer, when we face south, we look towards the center of the galaxy. So what we see is open clusters, globular clusters, and nebula. In the winter, where we face south, we go towards the edge. Well, there's much less to see there. So the Milky Way is a lot fainter as it goes through Auriga down Monocaris,
to Puvis. And whereas when you look south, it's so bright you could put your hand out and it will cast a shadow. When it's spring, you look above the Milky Way. And when it's autumn, you look below the Milky Way. So I actually like to have that perspective that, hey, I'm looking at the center of the Milky Way and this is what I expect to see. And if in spring I look up and this is what I expect to see, which will be galaxies. And to sort of make this point, here's a chart that plots all the Messiers. And what do you see is that here's the Milky Way, and where are all the galaxies in spring? Above the Milky Way. And in autumn, there are very few Messiers that are galaxies, but where do you see them? Below the Milky Way. Also, you see where are the open clusters and globulars and nebula? They're here. This is Sagittarius, and so this is where you'd be looking when you look at the center, and this is Orion, so this is the edge. Now, what you also see is where is it easier to find the Messier objects? Well, it would be in summer, because there are a lot of bright objects here, bright stars here, and there are a lot of bright objects, so it's very easy to star hop to them. The same as in winter. There's quite a lot of bright stars, and most of the open clusters and nebulae are very relatively bright, and so they're easy to go to. But in spring, line of sight, there aren't very many bright stars around these galaxy clusters, so it becomes a lot more difficult to find, and therefore, if you are doing a Messier marathon, you'll have a lot more difficulty going through the galaxies and Comma Berenices and Virgo than you would getting open clusters and globular clusters in summer. So that's something to take into account if you're just starting out to observe. Go for the bright stuff next to bright stars. When you gain experience, head for the galaxies. Now the galaxies close to Ursa Major are easier to get to because there are bright stars near it. The issue is that quite a few of us have finished the Messier Marathon, so what are your options? Well, one of them is the RASC Finest NGC objects, and you notice there are more galaxies and fewer globular clusters and open clusters, and a lot more bright nebula and planetary nebula compared to the Messier objects. Because the Messier objects got the brightest 110 objects, we're looking for another bright 110 objects, and the problem is that there are very few open globular clusters that are bright after we've sort of picked out 29 of them, so there are very few here. So when you start doing the finest NGC objects, we're going after more bright nebula and planetary nebula. There's the Herschel 400 list, and there are 8,000 NGC objects. Herschel had seen a little under 2,500 of them, and there was a club in Florida that tried to find more objects after the Messier objects. And they found 400 objects that they felt could be seen with a modest scope under moderately bright skies, or dark skies. And here you notice there are a lot more star clusters. And one of the reasons for that is Florida's at the 30th latitude, and they could go below Sagittarius and Scorpius and pick up a lot more star clusters and globular clusters. So here you see more of those and fewer nebula. But we didn't have any choice here. So like I have a predicament because I finished the Messier list, and I'm looking for more interesting visual objects to see, and I don't know if there's another 110 of them. I've only found about 50, 60 that I found visually interesting, at least based on my opinion. And so before you sort of decide on what you're going to observe, you've got to consider the aperture of your scope. The bigger your scope, the better it resolves, and the more light you could catch, and that's very important. And also the quality of the sky. And we're very lucky in Ottawa, because with an hour you could get to within a reasonably dark sky. In 2.5 hours you can get to a very dark sky. Your observing season. If you cannot observe in spring or autumn, you can't have too many galaxies in your list. And so you got to decide when do you have the time to observe and sort of pick your objects. And then the type of deep sky objects that are of interest to you, and you're interested in observing specks and smudges. So a lot of times if you like finding things, you may find you found things that aren't visually interesting. One of the ways you could avoid that is by looking at a star catalog, and so you get an indication of what you could expect based on the type of scope you have. Now, here are two galaxies, M81, M82. Now, M81 is a much larger galaxy, and its apparent magnitude is 6.9. Whereas M82, its magnitude is 8.4. There's a 1.5 magnitude difference, which makes this 4 times brighter. But it's 10 times larger. So that this 82 is a much brighter object to observe. And a lot of times when the transparency is good, I could observe this with my 7mm eyepiece on my 12-inch Dob, whereas this 10mm. If I go farther, I just do not gain any detail. And so just knowing the magnitude of the object is not enough. You have to know its size. And what a catalog does is also tells you the size of the object as well as its magnitude, and that becomes very, very useful information to decide before you try to star hop to it whether it's worthwhile seeing. Another point is that if supposedly these were 2 different galaxies, 13 mag galaxies, and I have a 12.5 mag scope, even though if these 2 are 13 mag galaxies, the odds are I'd be able to see this because it covers a much smaller area than this. This has greater surface brightness. And so in my 12.5-inch scope, this would be an elongated, faint smudge. This, in my 12.5-inch scope, I may or may not see. And if I see it, I just see the core, and it would be a very faint oval smudge. There wouldn't be much detail I could see out of any of them. But the odds are I would most likely see this. I may not see this. So it's sort of important to take into account magnitude and size. Now this is Hubbles classification, and again, all DSO catalogs will give you the classification of a galaxy as well as other kinds of DSOs. And so this is elliptical, and so it goes elliptical, and the second digit is its eccentricity, and so as the number goes up, it goes from round to flat. This is a lenticular galaxy, which is like a spiral galaxy, but it has no arms. And then here you have the spiral galaxies, and the spiral barrel galaxies. And the second letter determines how tightly wound the arms are and how big the nucleus or the bulge of the galaxy is. So as you go A, B, C, it becomes less, the arms of the galaxy are less wound. Now, there are pictures next to this, and what you would see, that if the galaxy was bright, that the most visually interesting ones are the spiral barrel galaxies and the spiral galaxies. The elliptical galaxies will just be bright smudges or faint smudges. There's very, very little detail you get out of here. But if they're bright, these would have a lot more visual interest. You may be able to pick out some detail in the arms. There may be some intriguing patterns, and so these would be of visual interest. However, if all these were dim, the ellipticals you'd still be able to see, and the likelihood is the spiral barrel galaxies and the spiral galaxies you won't, because its light is spread out. And the core would be smaller and have less light on it. So you could use the classification as well as the size and the magnitude to determine whether you'd like to observe this galaxy or not.
I'll do it from here.
Okay. Now, there's also a classification for globular clusters. And it goes from 1 to 12 in Roman numerals. And if the core is tightly packed, it's 1. If it's very loose, it's 12. And then in the middle, it's moderately packed. And so there's a scale that goes from 1 to 9 in Roman numerals, and the difference is how tightly packed it is at the core. Again, the ones, if they're bright, the ones that are more interesting are the ones in the middle that are moderately packed, and I'll be showing you some pictures of these. And the one that is loosely packed, you may think it's an open cluster or globular cluster. Now here's
Tightly packed.
a slightly packed DSO catalog. And here what you would see is the magnitude, its size, and the various classes. And with open clusters, they have a different system that I'll be discussing a little later on that are used for open clusters. So we'll take a look at M75. M75 has a classification of 1, which means the core is tightly wound. It's mag 8.6, and its size is 6 arc minutes. So you would say that this is a relatively big globular, or an average size globular, that's bright, but it has a tightly wound core. So what would you do if you'd be looking at it? You'd see a washed out core. You'd see a small, it would have a small envelope of stars around it, and you wouldn't really see much detail in it. If you go to M55, it's classified as 11. And so here, and it's brighter and bigger, so this would be and this globular would actually look like an open cluster, because its core would be very loose. If you look at 22, M22, you'd see a very bright globular, very big, and so there you'd see a core that would have a lot of nebulosity in it. A lot of its stars could be resolved, and the surrounding halo of stars would have a lot of stars in it. You'd see stars streaming out, and you may get a 3D effect from it. And so that is why it was basically found, and you can see it as one of the bright clusters, globular clusters. Oh, okay, now here's M55. No, here's M75. So you can see how tightly wound it is. It's overexposed here. You see the halo is much smaller relative to the size of the nucleus, and this star has very little detail in it. But if this was a star like this was further away, and it was Mag 12 or 13, the odds are you would be able to see it because a lot of its light is concentrated in the core. Now this is M13, not M22, because I couldn't get a good picture of M22. This is classified, has a concentration class of 5. And here, you can see the core has a lot of nebulosity in it. You could resolve the stars in it. You could see streams of stars around it. There's, the halo is very bright and defined, and the halo is bigger than the core. So this is a visually very interesting object to see. And like M22, and the reason why it is so interesting, it's very close. And so it is really a beautiful object with a core that has a lot of interest, visual interest. Now this is M55. And so again, you see a very loose core. You see some concentration of stars near the center. So, but it almost looks like an open cluster. And if it was Mag 13, the likelihood is you wouldn't see it in my scope because it would just be too dim. Now, here's an open cluster classification is different. I'll just quickly go into it. If it's strongly detached from the background, it has a classification of 1. If it's detached, 2. If it's weakly detached, it has a classification of 3. And if it is, you can't tell the difference between the open cluster and the background star, it has a classification of 4. But that's one letter used. It's the Roman numeral 1, 2, 3, 4. And then the open cluster could be rich. It means it has over 100 stars. If it's moderate, it has 50 to 100 stars. If it's poor, it has less than 50 stars. And then another characteristic used is in the collection of stars, is there a difference in magnitude? If there's very little difference in magnitude, it's class 1, a moderate difference in magnitude, class 2, and a great difference in magnitude, class 3. And again, this would show up on a catalog of dark sky objects and is useful information. Should I be pointing here when I do it, or?
Give me a
Okay,
nod.
maybe that's my mistake. Now, a lot of times when I observe, say I go to M, this is 94. Right next to it, I see 4618, 4410. I can't even read this myself. 40. So I see these two galaxies here, and I wonder, are they worth seeing? So I could go to a star catalog and check it out right away and see if it's worth going there. So what I like doing is I like going to an object that I'm familiar with and looking around the area and seeing if there's anything else worth observing in the area, and I go to the star catalog. So it was 4618, the galaxy in Canis Venensi, and I see that it is Mag 10.8. It's almost oval in shape, small, and it's a spiral barrel. There's no number here, A, B, C, D. So it's a lenticular galaxy that's oval in shape. And what's also interesting here is if I go down here, I see that the Clark and it's in the Clark and the Herschel 400 group. So that means that the club in Florida thought that it was at least in the top 400, whereas the other ones nearby weren't. So it could be a consideration, because how did they pick the objects? They looked at catalogs, and then they chose out of the 2,500 that Herschel chose. Maybe there were 600 obvious candidates, and then they went and observed them. And then they must have discussed it in a committee, and these were the ones they chose. Now the other was 4490. So if I look here, I see it's Mag 9864. This looks like it would be an interesting, and it's a spiral barrel galaxy, and arms are loosely wound. This looks like it would be a rather interesting galaxy to observe, and sure enough, it's the RASC has it, the Herschel group has it, the Clark group has it, and it's in the best NGCs. It would be interesting because it's reasonably bright, and there are loosely wound arms in it. The one next to it is much smaller, and it's dimmer, and it's next to it, it's an irregular galaxy. That would just most likely be an elongated smudge. But it would be really close to this galaxy, so it could be quite interesting. Now, that's basically it. I just have, wanted to mention one other thing, is that what do you do after you finish looking at the Messiers? Well, then you have to decide. I figure there are only about 60 bright DSOs to see after the Messier. If you want to do better, you have two choices: increase the size of your scope, or start
Bigger scope, bigger scope,
astrophotography.
bigger scope.
So one of those two things, those are your options. Thanks.
Well, hi everyone. It's going to be a hard act for me to follow those two impressive presentations, so I'm going to have to try and find another way to impress you. So maybe let's try with my brevity. What I thought we should do here is just take stock of some of the activities that we've done so far, some of the public outreach activities we've done so far in this International Year of Astronomy. And as you can see, there's been some planned events and some unplanned events. So we've previously talked about some of the planned events. We were quite privileged to be part of the IOA Canada launch with the museum here, and we also talked about the Café Scientific, which is another museum organized museums, I should say, organized event. The Museum of Nature and the Science Technology Museum, where I organized that together. Today, you're going to hear about two unplanned events. A school outreach event that occurred in Shawville, and also another event that we had a couple of weekends ago at Pinneys Point. Now, the event that happened in Shawville, I think that actually may become the gold standard of school outreach events, as you'll hear. It was very, very well organized, and I have to tell you, it was I didn't attend it, but from what I read and from how I saw the planning that was going through the email, the exchanges, it's quite something to see. I'm going to come back and talk about taffel music a little bit later on if Attila invites me back. But just one thing I wanted to say about some of the unplanned events. From my perspective, they're just as important as the planned events. These are the events that sort of pop in, and I think it says something about us as a center and the way that we can respond to them, but also the speed that we can respond to them. So I think we're servicing these requests for to come out fairly well, and I think we're getting better and better at it throughout the year. So I'm quite excited about that. The pace is picking up. Now, another thing that probably the next event on the radar, which I won't talk about now, but I'll certainly talk about through or still inform you through emails, is 100 Hours of Astronomy, which is really a global event. So the museum has an event that they're organizing actually at the same time of our meeting next in April. And I'll say more about that in an email to you. And likewise, I'm planning an event on the Saturday and maybe Sunday, if it's a rain, perhaps as a rain day, both as some solar, a daytime event, and an evening event. The International Astronomy Day, another event that is happening at the museum here. We're starting to line up a series of speakers for that, both the museum and us, which is turning out to be something exciting. The next really big event that I'm excited about, and not to say that these ones I've talked about aren't big, is the Galileo lecture. We've talked about before about the application process and so forth, and then the other items that you see on the list. It's interesting by the way, about the unplanned events. I think it was only 8 hours ago. I gave a outreach went to my daughter's school, and she's in grade 6, and I delivered a presentation. I spent tons of time organizing for this, because my daughter set such a high standard for me. I was so worried. So grade 6. So I went and reviewed lots of material, and I looked back on my notes, and so I got a skill testing question for everyone here, and I'm hoping that you don't get it. Otherwise, if you do get it, then I'm going to feel really bad about myself. So I had 2 questions that were asked to me that stumped me. Okay, well actually the first one I knew about. So it was, the question, people asked me to explain dark matter. No problem. It's so much in the news. The second question, somebody came up to me. I didn't even realize he was asking a question, but he came up to me. He kind of looked up at me, and he said, "What is the closest binary star system?" Anybody? Alpha Centauri? Oh, it's true. There you go. And I guess then you would know how close it is. All right, now I'm feeling really bad about myself. But it's something to see somebody, this little diminutive little fella, looking up at me and asking this question that I would not expect from somebody in grade 6. So just to close here, I do a lot of comparisons with what other centers are doing for outreach, and I think we're coming along nicely. I really still want to continue to pick up the pace, but with Taffel Music, as I'll talk about later on, I think we did a nice job, and things are progressing very well. Okay, so thanks everyone.
Thank you, Mike. Now to present the Deep Sky Challenge is Sanjeev. I will avoid trying to pronounce his last name. A very active observer who's got a really cool telescope.
Okay, thanks, Attila. Well, I've been a member for about 6 years now, and it's my first time up here. So thanks, Attila, for the opportunity. If you like observing faint specks and smudges, then I think this month's Deep Sky Challenge might be for you, especially if you like doing it with a moderate-sized telescope. I have a 14.5-inch Dob that I use. So my pick for March, we're almost into prime galaxy season, so it's actually a very compact chain of 5 galaxies. It's often referred to as Hickson 56, and it's a chain of 5 galaxies. The Hickson groups there's actually a list of 100 of these groups. They're put together for scientific purposes by Paul Hickson, who's a professional astronomer. He's Canadian. And, he picked these groups of galaxies that were roughly similar in magnitude to each other and were fairly compact groups and were interacting galaxies. They were fairly isolated from other galaxies nearby, and they were put together for the purpose of studying things like redshift and studying galactic evolution. But of course, with amateur astronomers, any list quickly becomes an observing list. And so there's probably a good 20 or 30 of these galaxy groups that are observable with moderate-sized telescopes, but by which we're talking 12-inch to about 16-inch sized telescopes. So I've just put together 3 steps here, and I'm going to show you some star charts about how to get to this group. And at the end, I'll show you a little photo of it as well. The galaxy group is in Ursa Major, and it's very close to a fairly easy to locate galaxy called NGC 3718. So the first step is to find that galaxy, and then we just look a little bit to the south of that galaxy using high power, at least 200 times, and you'll see the group as a combined glow. And it's actually five galaxies, but I've never seen more than 3 of them. So if you can see at least 2 clumps, then I think you've pretty much met the challenge. Okay, so this is this chart here just shows the Big Dipper, and what we see here is a Telrad circle, It's 4 degrees across. This star here is FAD. This DSO here is M109. Now, the stars here are down to about Mag 7, so you should not be trying this, unless you're under a reasonably dark sky. For me, green zone on the light pollution map is bare minimum, so I personally wouldn't try this at FLO. I would try it a little bit further west of the city. So, you're talking about a limiting magnitude of about 6.5 would be very good to try this. So this is the tail rat circle, and right where the middle circle there is, that's really where the group is located. This chart is good if you're using a optical finder scope. Your optical finder scope will usually show you stars down to about Mag 10 or 11. Now, I don't use an optical finder scope, so I usually skip this step. But if you do use one, you should find a chart that will show you stars down to about Mag 12. There's a bright star here and here. This is about 3 or 4 degrees apart. This is a naked eye star, so you can easily just star hop here straight with your tail rat if you're not using an optical finder, or you can use these background stars as well. Now, this chart shows you the two main galaxies you're going to see easily. This chart here shows stars down to Mag 15 or Mag 16. Personally, I would suggest just using a tail rat to zero in on these two galaxies and then just looking in your eyepiece. But what we have here is NGC 3718. It's the big galaxy that I told you is a Mag 10 galaxy. And just a little bit to the south of this galaxy, you can see the Hickson group. There's 5 galaxies here. There's 4 of them in a very tight chain and 1 right here. And they're rated between Mag 14 and Mag 16, depending on what source you're consulting. So they're typically the faint specks and smudges I see in my telescope are Mag 15 galaxies. Is something that's doable on a good night. These 2 in the middle here that are visible in my scope fairly easily. I've actually seen this one here. This is the brightest member, but it's got low surface brightness, so it's hard to see. This is Hickson A. They go in order A, B, C, D, and E. E is the last one. So most likely you'll see 2 of these. The B and C members you'll be able to see. And A you might be able to see with averted vision with a lot of difficulty with high power. Now, the thing to note about, I'm going to show you a photo first, and I'll come back to this chart. This photo is by Jim Burnell, and this is used here with his permission. I like this photo because it's black and white. Now, this is NGC 3718, and what you see here is the Hickson group, okay? So the distance from here to here is only about 6 or 7 arc minutes in an eyepiece. So this is a very compact group. You're not going to see this level of detail in the eyepiece. What you will see now, you have to use about 200 power, 250 power to see this. The way I look for this group is I look for these 2 stars. And you look at the core of this galaxy, look at these 2 stars, and just try to stare at this spot or a spot nearby to use averted vision. If you go back here, the thing about this whole area is that each box here, it's very important to know how much space you're seeing in your eyepiece. This box here is about 15 arc minutes wide, and the height of this box is about 5 arc minutes. So this whole group will fit into about a ½ degree circle in your eyepiece. All right? So it's important to know as well where north is. On this chart, north is that way, and east is this way. So if you can know which direction north is in your eyepiece, then you'll be able to sense which direction to go south. And if you're trying to identify these galaxies, then you really need to know which way is east and which way is west, because this is the easternmost member of this group. And the thing that's interesting about this is that I know it's only a faint speck, but this galaxy and the other galaxy I showed you, which will be around here, these 2 are interacting pair about 40 million light years away. This group is 10 times further out. It's about 400 million light years away. So being able to sense that in the eyepiece and just that juxtaposition is quite the thrill. So even in visual astronomy, as most of you know, it's not necessarily what you see in the eyepiece, but rather what you understand from it. So that's the Deep Sky Challenge for March.
Thank you, Sanjay. I'm personally a fan of faint specks. Anyone else agree with me? Okay, we have observations of many faint specks now. We have, in fact, 10 people. We have a lot of active observers here who are going to observe. Can I ask these people to get ready after you see the person ahead of you to stand up and stand here by the aisle so we can switch speakers very quickly. And Sanjeev is already ready.
Okay, so this is, I'm kind of new to astrophotography. This is the comet Lulin. This photo was taken, all the photos, I'm going to show you 3 photos. They're all taken with Canon DSLR with an 85 millimeter refractor. The comet is...
Can you dim the lights?
Yeah. This photo was taken on February 28th. And I don't know if it really shows up here, but there's actually 4 little faint fuzzies right here, which kind of interested me more than the comet. I don't know if you can see it, but right there is NGC 3020. That's 3024. There's 3016, and in the middle there, you can actually see a Mach 15 galaxy, which is 3019. Now this comet here, this field is about 2 degrees wide, and it was actually just passing through Leo when I took this photo. This is a galaxy trio which is very popular for visual observation. It's called the Leo trio, which many of you I'm sure have seen. That's M66, that's M65, and that right there is NGC 3628, and they're about a degree apart. And this is, all of these are 90-second exposures. This one was a stack of 30 exposures put together. Where's my next slide? Oh, there it is. This is my first real attempt at the Orion Nebula. It's about a 2 degree wide field, and this is again using all these are unguided exposures. So this is about 40 90-second exposures put together. So it's about 1 hour's worth, and this is kind of where I learned a bit about processing, because I use a software called Nebulosity, and I was able to get some of this stuff to show up. And this thing, as you know, is the Running Man Nebula. It's the NGC 1977, and here we see 43, and this is 42. This is a sword of Orion.
Thank you very much, Sanjeev.
I actually had some time to do some observing in February. The observing report section is a problem for visual observers because mostly it's a forum for the astrophotographers to show their wonderful images. But visual observers like me, well, you know, we don't take pictures, so we just kind of have to believe that we saw what we said we saw. This time I thought I'd take a few pictures to enhance my credibility. Think of these as snapshots because they haven't been going through the multiple stacking and image processing effects that all the real astrophotographers fall. In that case, I saw a very beautiful crescent moon in conjunction with Venus. What's really cool about this is the moon's crescent was kind of bowl-shaped, pointing straight up, and it was a very sharp crescent with beautiful earthshine, one of the best earthshine I've ever seen. And the reason was because, in this case, the moon was fairly far away from the sun and directly fairly high in the sky, because the ecliptic was nearly perpendicular to the horizon. Also, I spent a fair amount of time observing the winter Milky Way. This is observing out toward the edge of the galaxy. You can think of it as towards the unfashionable eastern side of the galaxy. Orion was very high in the sky. Here's Orion if you have trouble finding it. And here's Canis Major and Lepus, the hair underneath Orion, and Canis Minor, Gemini, Taurus, and Auriga. And you can see the Pleiades just below Taurus there. It was a beautiful sight. I spent a long time luxuriating in the night sky watching this scene. Oh, there's Perseus. We're zooming into Orion a bit here, and you can almost barely see it. There's an arc near the top of the image.
Right here, just very slightly pink. This is just the beginnings of the detection of Barnard's Loop. This snapshot was taken with an ordinary digital SLR for, I believe, 120 seconds at f1.4, I believe. I'm going to zoom in a little bit. Oh, here's the Orion if you can't find it. Zoom in a little bit. And the reason I'm showing you this is I spent a fair amount of time observing the Horsehead Nebula visually. It shows up rather easily in this rather cheap photo. I was able to see without the filter, no filter at all. Everyone says you must have a $200 hydrogen beta filter. I was able to see in the 16-inch telescope quite easily. Mind you, it wasn't a spectacular sight, but it was detectable. And of course, I spent a long time luxuriating in the complexities of M42. This streak, by the way, is not a scratch on the film. This is probably a satellite pass. This is Canis Major. Here's the outline of the constellation. And this is the heart of Canis Major, the heart of the dog, the M41 open cluster. But I have this picture here to remind me to tell you that I was observing Sirius, the star, because Sirius is a double star. It's one of the most difficult.
You're popping, yeah.
Hubble stars to observe because the primary is so bright and the secondary is so faint. But the scene was terrific. It was excellent. And I was able to see the pup, they call it, secondary, in a telescope as small as 10 inches. Now there's the outline of Canis Major, so you can kind of identify the stars. The Pleiades and Hyades were fairly high in the sky and were very nice to see. You can see on this snapshot, which is again only about 3 minutes long, at f2.8 or so, ordinary camera. You can see the beginnings of Brewster's Nebula. That's the reflection nebula in the Pleiades. And up here's the Hyades. And I also spent a fair amount of time watching Comet Lulin, although I was really confused because one night it was near Saturn and the next night it was gone. It moved 10 degrees in one night. I finally found it next to Regulus. And one thing I didn't notice visually observing, but there's an 11th magnitude galaxy right beside Regulus. I have to look that one up again. That's a single frame, by the way, no stacking or image processing of any kind other than contrast adjustment. And finally, at 4 a.m. in the morning, it was really very nice to watch the Milky Way core setting behind the trees. And just to help you get oriented here, here's Scorpius and Sagittarius. Oops, yes, Scorpius and Sagittarius. Now at this point, you should have figured out that something is fishy here. Yes. Okay, first of all, the moon never does this. The ecliptic is never straight up in the air, and the Milky Way core galaxy never sets behind palm trees in Ottawa. That's because I was here. I just want to point out that this stuff here is water, but it's in the liquid state. This is not snow, it's coral sand. Actually, this is just a setup for a talk that we're going to give in May. Bob Olson spent a week at this site taking real astrophotos. And I've talked him into treating his astrophotos. When he returns from gallivanting around the southern United States in a relative idyllic paradise, when he comes back to Ottawa, he's only going to come back when it gets warm, but when he does, he'll bring his pictures with him. Okay. Next is Paul Commission. Would you like to speak from your chair, Paul?
Yeah, this is the famous Splinter galaxy. It's in Draco, and what was mentioned before, I should also mention the fact that it's important with a lot of these galaxies, not only their type. This is an SB, but the fact is you're seeing here it's on edge on rather than face on. So the position, it's always easier to see a galaxy edge on than face on because you have the center part, the bulge especially, is quite bright, as you can see. This is 10.38. It's in the constellation Draco. Although Draco is a circumpolar type of constellation, I rarely do any transpolar observing. So this time of the year, you can see it low down in the north. But this was taken last fall. But I thought I'd show, this splinter galaxy is extremely thin. It's about 12 arc minutes long, but only about 1.2 arc minutes wide. Okay, next one. This is also from Draco, and I thought I'd show the various types. 5981 is on your extreme right. Now that is an SB also. Now you notice that's an edge on. The one in the middle, 5982, is an elliptical galaxy. And like the previous speaker said, you notice that it's just a round smudge. There is no form to it really. And on your left is NGC 5985. Now that is a spiral seen almost face on. So you see the position, it's observing galaxies or photographing galaxies. It's not only important to know the types, but it's also important to figure out their position, their tilt as they call them. And you see the one on the extreme right is tilted such that it's edge on, and the one on the left is almost face on. And the one on the 5981 on your extreme right, that's a 13th magnitude. That's pretty hard to get. But the one in the middle and the one on the left, they're around 11th magnitude. That you can see fairly easily in an 8 or 10-inch telescope.
Thank you, Paul. Next is Gary Boyle.
Thanks, Attila. Oh, unlike Sanjeev and Attila's pictures of Comet Llewellyn, mine was stacked. You took about 156 images of 8-second images and stacked them together. So really what it showed is once I stacked it in registacks, you can actually see how, almost like a movie, how fast the comet was really moving. And you can just see by the blur of stars. So this comet was really buzzing around. Pretty well the quickest comet other than Arecibo-Elcock back in 1982. It took like 3 nights to move across the horizon. And some lunar shots. Rima Pretorius. Pretty well when the moon was about 3 or 4 days old. I don't get to see it because sometimes when the moon is that young, it's usually behind a house. And transparency was pretty good that night. And again, this thing with the 12-inch Meade LX200 at f10 with the TU cam and stacked with Registax and Mare Crisium. And last but not least, Venus is putting on a great show. In fact, when we had the TAFL concert last Friday, I was showing Venus about this phase to about 70 people before the concert, and then it was cloudy after. I was able to catch the mosaic of 3 nights, and yes, this was yesterday. Paul didn't believe me. I was observing at 4:45 in the afternoon. It was a little hard to find Venus. Has anyone seen Venus this thin yet? In this, yeah, it's a little hard to find now. Definitely go-to telescopes will really help. Yeah, so that's it for my montage. Just as a little spoil, I guess, for next month, since it'll be the 100 hours of astronomy during our talk over here at the museum. If it's clear, I plan to be home that night, astrocasting. Hopefully we can show it here on screen, breakaways, what am I looking at now? And now be through SparkCast. So cross your fingers for next month. Thanks.
Thank you, Gary. Next up is Gordon Webster.
Well, in early March, we had something I haven't seen at all. This whole winter, we had 3 nights in a row where it was actually clear. Gave me an opportunity to look at Ceres, and it was very easy to find up near 54 Leonis. And on the first night, nope, that's not the one. There it is up, where'd it go? Yeah, right over there, okay? And the next night, which was almost exactly 24 hours later, it had moved to there. And the third night, it had moved over there.
We have animations.
And we have yep. Okay, do we have one with all 3
We do.
together?
Oops. Attila and I are both pushing buttons.
Okay.
That's with all 3, I believe.
All 3 together. What I find interesting is these 2 are almost exactly 12 hours apart, or 24 hours apart, and this one is 25 hours. And you can see here that this is a larger gap. And some of the reading I was doing, someone suggested that if you looked at it about half an hour apart, you could actually see that it had moved a noticeable amount. So, and that's no stacking involved other than to animate it, because it's a sketch. Okay?
Thank you, Gordon. Next is Hugo Lima.
Okay, from being at a galaxy far, far away, I thought I'd bring you back down to Earth. Back in February, I saw at sunset a sun pillar, and I don't recall seeing one quite this sharp. Now, as usual with serendipitous events, by the time you get a camera, things have changed. So it almost disappeared here. And however, the phenomenon, I understand, it's quite different than normally you see clouds and solar rays kind of fanning out due to perspective. What this looked, it looked much sharper than it does in the picture here, but it's a straight column or pillar straight up. And as I understand it, it's caused by reflection of sunlight off ice crystals which are oriented horizontally and are descending slowly down. So it's quite different than the refraction kind of effect that you get with rainbows. Okay, thank you.
Next is Robin Woods.
The last time that Venus was the evening star, just over a year ago, I tried photographing it, but from my property it's in the trees. So I had to drive to my son's, which is a bit of a pain. And finding it and photographing it at night, I find that the contrast between that and the sky is too much. So I decided I have a go-to telescope. Why not do it at lunchtime? So this was taken today around 1:13, and I've been doing it over the course of the Venusian year. It's taken through a Teleview Pronto with a 3x Barlow and a Nikon Coolpix 4-500. I took a movie and then stack them in Registack. So this is about 117 frames stacked, and the magnification is about 800, believe it or not. So I have a collection of these going back to the last time it looked like this. Thank you.
Thank you, Hugo. Next is
Okay, so last night, well, 3 o'clock this morning, one of my variable stars was going into eclipse, so I had to be up observing. So I was wondering, what am I going to do for a few hours before I have to load the other scope on the mount? So I decided, I was looking at my planetarium program, and I noticed a whack of comets. So I took a bunch of comet pictures. This is the first time I've ever tried to actually observe 5 or 6 comets in one evening. So you guys can look for the comet in there while I tell you about Comet Biothin. It's discovered in the Philippines by Reverend Leo Biothin back in 1975. It turned out to be a periodic comet, came back in 1986 and was viewed. 1997 it came back, but it was a particularly bad apparition where the comet was mostly on the other side of the sun when it was closest to the sun, so it wasn't seen. So here it is back for its next apparition, and you won't see it because it got lost somewhere along the way. I didn't realize that until after I had done 45 minutes of exposures, and I couldn't find it in the frame, so I went hunting online. And it looks like it's one of these comets that either broke up sometime, like perhaps in 97 when it was close to the sun, broke up and vanished, evaporated. So what we are actually looking at here is a dark nebula. It's a dark cloud of dust that's obscuring some of the Milky Way stars, and no comet. Next slide. Comet Cardinal. This one is about, let's see, I got notes here, 12th magnitude. Comet Lulin, you hear a lot in the news. They always give you this impression that tonight the comet's going by. Got to get out and see the comet tonight. The green comet, because no comets have ever been green before. But Cardinal, you can see it's small, it's relatively faint, but it's decidedly green. And a nice little open cluster nearby. Next, Comet Broughton. I tried to get some color frames of this, but this guy is so faint that the color images were just really poor. So I stuck with a black and white one for this guy. And again, nice little open cluster down in the corner of the frame. Next, let's see, Comet Kushida. Was found by a Japanese fellow back some years ago. One of the Japanese comet hunters. They're very famous for being comet hunters. And so again, you can see it's green. There's a lot of noise on this because it's relatively faint. And I was just banging these things off to try and get them all in. But what I thought was kind of interesting was this little red nebulosity down there, just to add something to the frame. Next. Okay, Comet Lulin. Well, everybody's doing Comet Lulin. Again, it's green. Nice tail on it, you can see at the bottom and stuff. I got little bit of cloud was coming through while I was taking the shots. What happens on these pictures is, of course, I'm taking multiple exposures and then I align them all on the head of the comet, which means all the stars all get trailed. That's why we get these this effect. And the next one. This is Comet Wild, number 4. He was, or is, a Swiss astronomer who picks up a lot of these things. And this one's about 13th magnitude. And I marked it. It's not green, but it's quite faint. So what I thought was interesting, unfortunately we've already done our challenge for the month, so I can't challenge you to go see these, but I could defy you, or I could encourage you to set a goal with the 16-inch telescope out at FLO. Quite conceivably, you should be able to see the 5 that I caught, plus Churyumov Chesame, I can't even remember it, but the double Russian name is also in the western sky at sunset. Unfortunately, by the time twilight ends, it's in the trees at my observatory, so I couldn't photograph that. But so conceivably, if you wanted to go out to FLO, you could pull in 6 comets in one evening visual.
Rick, you just have to submit your observing challenges before midnight the previous night.
Yeah, I apologize. I was still shooting these at midnight last night.
Yeah. Excuses. Next is Rolf Mahner.
Where's the remote control channel change machine? Okay, so first is a series of what you might call, there's 2 what you might call Murphy slides. So this was actually taken in January, and it was really cold, so I thought I'd try something through the window, and that's what this is, so you can see the outline of the window there. But so this is 4 20-second exposures combined, and you can pick out Orion, of course, and the sword of Orion and the belt there. But then I discovered that there was something peculiar there, and there were these odd green things that really are not in Orion. So evidently, when you take a picture through a window, you're going to get some peculiar kind of reflections there too. So that's something to keep in mind, or to try and figure out where the reflection is coming from and try and stop it, I guess. I don't know what the source was, but anyway, that's that. So I guess I got to point it at the thing. No, that doesn't. Why isn't this advanced? Oh, there we go. Okay, so this is another what you might call Murphy slide. So yeah, okay, so there's maybe a little bit of trailing in it, but so what makes this a Murphy slide? So it's NGC 3077. Well, it was supposed to be a really spectacular picture of M81. And the thing is, M81 is like maybe about one diameter of this frame away. And yeah, so I lined it up in the finder scope, and yeah, that looks like M81. And then I took an exposure through with the camera for about a minute to see if that was actually it. And yeah, there's a fuzzy thing in the middle. So okay, so I'll carry on and take another 40 minutes of exposures. And so then I stacked it, and boy, that's horrible. But it's just basically this nondescript elliptical galaxy, and we were talking about how they're just smudges anyway. So that's what that was. And it wasn't M81 at all. So I discovered that, by searching in the area, and that was that. Oh yeah, so this is the moon. It was about 3 days old, and it's the entire moon there. So this is again part of the series of trying to make a mosaic of the entire moon, and just eventually we'll combine all the areas where the craters are well defined. And we can actually zoom in on a little part of this. So one frame is actually fairly detailed. This is just a single picture. Now, because it was just a 3-day-old moon, there was quite a bit of earth shine on that day. So I took a series of exposures ranging from about 1/40 of a second to 4 seconds, and I combined them with this result. what's important here is that if you were to try and expose just for the Earth shine for 4 seconds, the bright part of the moon would be washed out, because there's a difference of exposure there of about 200 between the darkest part and the brightest part.
Second roll. We have an ooh and an ah for this image because I think it's fabulous.
It's very cool.
Ooh. I think this is astronomy picture of the day material. Awesome image.
So it was quite a bit of work because of there's something called HDR, which is high dynamic range photography, where you combine these high dynamic range pictures. But of course, there's nothing for it to align to when this part is completely overexposed, and this is not even visible in some pictures. So that doesn't work very well. So this is a very manual procedure actually to do this. But what can we see here? This is almost like a full moon, right? So this is very interesting. So I'm just going to point out a few of the features that actually show up on the dark side, and so just what we see there. So Aristarchus and Grimaldi are probably the brightest and darkest craters on the moon, and they show up quite well. Mare Orientalis is the largest impact basin on the moon, which you hardly ever see. And sometimes during it depends on the libration of the moon, you see. So Grimaldi and Mare Orientalis are sometimes so far over that you can't see them, but it just so happens that that they were in a good position here, and like this basin here is just like a large number of concentric rings, and you can see that it looks like there's a bite out of it, but actually it's just a very dark part of the basin. And of course, Tycho and all the rays coming out as well. Again, it just shows that still a lot of detail in the cratered part of the moon. Okay, so what else? Oh yeah, so there's Comet Llewellyn, 20 minutes, and it did trail, of course, in the 20-minute exposure. So I thought I would also do individual exposures and combine them. So this is actually kind of an enlarged part of this. Is just with a telephoto lens, and it's kind of cropped and enlarged from that. So instead of doing a single 20-minute exposure, I combined 4 10-minute exposures. But it looks horrible because of all the stars, and they're just blobs. So I thought, what can I do to get rid of the stars? So one thing I did was I applied a filter which removes everything that looks like a point source, and it doesn't work perfectly. It kind of turns the stars into donuts, but it does certainly attenuate the stars quite a bit, and you can do a little bit more processing to bring out the outer parts of the comet. And then I tried another technique, which was basically stacking and doing a kind of stack that doesn't combine the stars. So this is a stacking of the same thing, but it didn't stack the stars, and it was just a magic way of doing that. So that's all. The stars are almost gone there. I think that's it.
Kiro.
Yes.
Okay. All right. Here's my Comet Llewellyn, not green. All right. It's just a little sketch that I did. I was kind of curious to locate it once and kind of score it for the observing log. I went around and checked the star numbers. So I've got the comet very well located there. That was in working with 10 by 50 binoculars, and that was in Virgo. That's the one I had mentioned earlier. Okay, we'll go to the next one, please. All right, Asteroid 1 series. This is what Gord Webster was showing you with his beautiful, I just love that sketch where you could see the movement across the 3 nights there. And I just have it for the, I was observing it on several occasions, but I just made the one sketch of it here. This is, remember we were talking about there's 54 Leonis, and it's kind of a triangle of stars. There's the apex, there's these 2 at the top. and the asteroid is now sitting over here. But when I saw it, there's that triangle of stars with 54 at the bottom. One Ceres was over on this side. Now, when I was looking at it, I think I marked 10 by 50 binoculars. I was looking at it with the binocs, but I also then put it in I had it in my C11 telescope at very high magnification, and I could detect a disk diameter on it, and I could also detect a faint brownish yellow color. Now, Ceres is the first asteroid that was discovered. That's why it's called 1 Ceres. It's about 930 kilometers in diameter, and it accounts for about 25% of the mass of the asteroid belt. Right. So, and the other things, I went out one night and I was just looking. One of my main target was going to be Ceres, up in this area right here. But of course, there was a Lulin was sitting down this way. This is just my finder sketch. That's my preparation ahead of time. Okay, I was one of those. All right, and I was observing Saturn down here, and like I say down here, this is exactly how I saw it. It's quite the image. Okay. Quick update. Some of you may know that my wife Bridget's just in the back there, and our daughter Emily has been up in Eureka at the top of Ellesmere Island, or 3/4 of the way up Ellesmere Island. Yeah, she said the North Star was almost directly overhead. So what she was doing was she was out there with the University of Western Ontario working at the LiDAR facility. This is a light-ranging laser, so looking at particles in the atmosphere. And the Pearl, as it's called, laser was working a little bit on a clunky kind of schedule. It was they'd have a few breakdowns, they'd fix it, and they kept it running. But on this current campaign, they actually got 17. Was it 17, Bridget? Yeah, 17 observing runs with the LiDAR, and that's the best that they've ever done there. And just a couple of days before she was coming home, the LiDAR broke down, and that was it. It's kaput, and the thing is quite old. So, but anyway, Emily was maintaining a blog site. So there she is at work in the control room for the observatory, which we can see. That's at her base camp here, but that's the observatory right here, PEARL, Pearl, with the moon in the background. These are all low res. I just ripped them off her blog site. And of course, she'd always heard that if you go up into when you've got minus 59 temperatures, minus 50 temperatures, if you take a cup of hot water and throw it in the air, what happens? And she said it was unbelievable. She threw this bucket of hot water up, and it just powdered in the air and just fell down as powder. So, all right, that's the Emily update. Okay.
Thank you. That's our observing update.
Yes, thank you. Thanks for letting me do that. Yes.
Next, it's the Brian McCullough Show, and here he is again.
Yeah. I could put a mask on, right? Okay. All right, so we're going to be looking at, I've picked another object off the moon. Could we skip back to Rolf's nice combined image of the moon there, please? Just for a sec. All right. This illustrates perfectly what we're looking for. So the challenge that I'm putting forward would be to observe the area of Aristarchus. And Aristarchus, as Rolf pointed out, probably it's the brightest object on the moon, the brightest area on the moon, and you have a nice contrast with Grimaldi, the darkest, side by side. But this is the area where we'll be looking. You have the Imbrian Basin here, the Sea of Rains, and there's the Sinus Iridum, the Bay of Rainbows, and there's the crater Plato. So then we have you come down from the Apennine Mountains, there's Copernicus, and then you also have the crater Kepler that's shooting rays all up. So it's quite a nice walk around, but it's almost, you can see like an outer ring of the Imbrian Basin. All right, so we'll skip ahead to, thank you. Okay, so what we're looking at is the Aristarchus Plateau and the Schroeder's Valley area. And if you have one of these Ruckel moon charts, the book of all the moon maps, how much are they going for on eBay now? We got them all for $9.99 at W.H. Smith & Son. They're going for hundreds of dollars on eBay, I hear. So, anyway, so Ruckel chart number 18. So we'll go to the next one, please, Chris. All right, looking at Lee McDonald's. This is why I wanted to jump back to Rolf's, because it was a much different presentation of it. But even on a bright full moon type image, you can still see how bright Aristarchus is there. Okay, let's scoot ahead to the next one. All right. I was talking to Gordon Webster. He was talking about his Ceres. I'd asked him if he had observed Ceres. So he was out looking for that, and then he told me he had seen something else. So I was trying to figure out, well, what is it that he saw? Probably Aristarchus. And he goes, no, it was actually something else that he ended up observing. We'll hear about that another time. But he said, no, he had observed Aristarchus the other day and made a sketch. So I said, well, send me the sketch. So here's a sketch of the Aristarchus region with the craters Aristarchus and Herodotus, and I'll show you some points in just a moment. And that's the area we're looking at in the moon. Okay, we'll go to the next one. So this is not any one of our photographs, all right? But you can see that Aristarchus is, what's making it so bright is the underlying material. So when the impact happened, it's a relatively young crater on the moon, and when the impact happened, it threw all this fresh material out, and it hasn't darkened in the radiation. The radiation that's hitting the moon all the time eventually will darken all the regolith, all the material that's on there. Okay, and we're going to be looking at a couple of things, including this wall, this Rupes Toscanelli, with the crater Toscanelli up top here, and there are these rimae, these trenches, all right, that are running off from the Aristarchus plateau here, and of course this big guy right here. So we'll go to the next one, please. One thing I wanted to point out, they talk about the Aristarchus plateau. You're looking at a 200 kilometer by pretty much 200 kilometer, almost square plateau. And you can see this is after some of the impacts that happened on the moon in the region, and you had the lavas running like liquid motor oil, filling up all of the basins, the large basins. Well, eventually all of that started to cool, but then you would have these lava tunnels where at subsequent periods, more material would come bubbling up and they would lay fresh material, fresh deposits on top of what was already there. And usually you can see that there's very light cratering, so it's still relatively new material. And we'll go to the next one, please. All right, a couple of interesting features here. Okay, to give you some scale, Aristarchus, 40 kilometers in diameter, and you can see Herodotus. And note the difference in the albedo, the reflectivity of these two objects. And the Schroeder's Valley snakes around, well, you can snake it around this way if you like, because this is what they call the Copperhead right here. And this is probably, the best guess on this is probably a collapsed lava dome, or lava tube, I meant to say. So this is where lava had been piping up through to the surface of the moon from down below, and eventually the top of the tube collapsed. Something else very interesting is Mons Herodotus, and that would be a very interesting thing to see if you can pick that up in your telescopes, the little mountain that's sitting right there. And there's a lovely little mountain range, Montes Agricola, that runs right across the top there. All right, so. But this is the view I like. This is from the Apollo 15 spacecraft, and you can see we're looking at it from the opposite direction now, and with Aristarchus here, and there's Herodotus, and then you can see the collapsed dome here. It's quite a structure, so if you have a chance to observe it at slightly different lighting angles, I think you'll be well rewarded for your effort. All right.
Thank you, Brian. I'm surprised you didn't describe that as a man with two eyes and one running nostril. You usually have some bizarre interpretation.
Yeah, a lot of people see that as cat's eyes, right? Okay.
Right. Astronomy is not only fun to do yourself, it's fun to bring it to other people. We have three reports from people who have done just that. We call them public outreach reports, and this is a continuation of the Brian McCullough show.
Well, Richard's going to...
We thought we'd do this one together, and we actually haven't figured out exactly how we're going to hand the mic back and forth, so we'll see what happens.
But just sit down.
That would work too. Brian and I ended up visiting this school in Shawville, Quebec, Dr. S.E. McDowell Elementary School, and did an outreach program there for a grade 4 class. And we had a ball. It was a lot of fun. But we thought we'd actually go into a bit of detail about what was involved in putting it together in order to encourage you to do it, because it's worth doing. It was fun. The kids loved it. We loved it. Brian loved it so much that he actually ended up doing a second outreach session afterwards in the cafe in Shawville. I wasn't there. I had to leave, but we just couldn't shut him off. So we thought we'd share some of the tips with you on how to put things like this together. This one, it took about a month and a half to organize. This is kind of the paper trail afterwards. It started with an email question that came into the site, and it was a school teacher And one of her students had asked her, how come if there's no gravity on the moon, how come the lakes, the water stays in the lakes? It's a good question from a 9-year-old. And so, well, you know, it's like going to a medical convention saying, is a doctor in the house? Right, well, this came into the email and it was forwarded onto the council list. So 900 astronomers jumped on this poor school teacher and started spewing answers at her. Brian kind of took the lead on coordinating those answers and gave her an answer that was suitable for 9-year-old kids. And then at some point, Mike said, would you be interested in having somebody come to your school with some telescopes? And she, oh yeah. So then it became a coordination exercise, and it took about a month for us to work out when we could come, when the school was available, when Brian and I were available. We were trying to find a time to go that the moon would be visible in the afternoon sky so that we could do some outdoor observing. And we couldn't make that happen. The moon just wasn't cooperating. But we thought, well, we could always revert to solar observing to have something to look at outside. And besides, it'll probably be cloudy anyway. So we set a date and we went. We ended up going on February 25th out to Shawville. We were visiting a classroom. So here comes the advice section. The first thing is you want a lot of information about what your audience is, what type of kids they are, how many, how big. Do you need a ladder if you're bringing a telescope? That's the kind of thing you can't afford to forget. So we worked out a bunch of questions. How many? 24 kids, grade 4, that's age 10 to 11. They're about so high. So if you have a tripod-mounted telescope and it's low, that's okay. But you know, if you've got your 37-foot high Dob, you'll need help. Anytime you're dealing with kids in any kind of public capacity, if you're planning to take pictures, you need to find out whether you have permission to do that, because a lot of parents are concerned about pictures of their kids ending up on porn sites and things like that. So we got official permission from the school, and in fact there was one child for whom we did not have permission to take pictures, so she's very carefully not in any of the photos that we're going to show you. So you need that type of information to avoid trouble. Brian got a list from the teacher of what specifically was in their curriculum, what were they supposed to learn about, and it was just a nice little simple list, you know, everything about the moon and craters and the solar system and planets and stars and galaxies. And we have an hour. So Brian didn't think that was a challenge at all, and he put together a program. And we wanted to do an indoor and an outdoor program. Indoors, classroom stuff to hit them with the knowledge they were supposed to learn. And an outdoor program because we wanted them to be able to touch and use a telescope. We thought that was important. Unfortunately, there's no daytime moon available. Getting kids back to school in the evening for night is basically impossible. Forget that. So we decided to go with solar. Now, of course, there hasn't been a sunspot seen for about 8 years, so white light solar is just a waste of time these days, but we thought hydrogen alpha is always a good bet. You can usually see something, so we brought a hydrogen alpha setup as well. 10, 11-year-old kids have an attention span of about 15 seconds, so you need a program with a lot of change in it, a lot of varying, a lot of stuff to do. Brian brought a truckload of plasticine and toys and gadgets and gimmicks.
It matches my attention
and it was perfect, yeah. And what were we saying? Oh yeah, and so Brian ran the indoor program and I did the outdoor, and so he's going to talk about the indoor program. Here it comes. I told you we didn't rehearse this. So.
Okay.
So
All right, just very quickly here, start off with a short slide presentation just to give the students some idea of where they fit into the universe. So that's what's going on up in the first slide there. But then, since we couldn't, as Richard was saying, we didn't have the moon during the daytime sky, so we set up a small telescope, a small refractor in the classroom, and set up a poster of the moon, a map of the moon, and it works as a very, very good simulation. And what most of the kids will comment on is the words are backwards. They'll notice the labeling is reversed, and then you can start to tell them a little bit more about how the optics will start to flip images around. We made little pocket sundials, and we were fortunate that we had a sun outside because Richard was out there. He'll tell you about that in a moment, but we were able to go out and work with the little pocket sundials. So we made those into class ahead of time. We had to make moon craters in plasticine. So we just take some plasticine, a little base, they make their own lunar base, and I said, and if you want to, you can make little aliens to go with it well. Look out, right? And I took, now the plasticine I could have taken gray and brown, would have been very nice like the moon, but I went and found all these neon colored plasticines. Looks fantastic, right? We did a meteor impact experiment after, I think that's in a slide in a minute, yeah. But we also did this little exercise where Ron St. Martin very kindly gave us a little bundle of some fragments from meteorites that had been, when meteorites were being cut into samples, and all basically the sawdust from these meteorites, he was able to get some. And he donated it to us so that we could use that for some public outreach. So it basically printed off these little cards on form business cards. So you're seeing on the top, you're seeing the front side, and on the back, on the bottom, that's the flip side of it. And what I did was, it says these meteorite fragments were left over from samples cut from meteorites that fell in North Africa. So it gives them a bit of information about the fragments. And that little white box there, they put some white glue, just put a dab of white glue in there, and they sprinkled their fragments. We gave each kid a little plastic bag with fragments. They sprinkled them in, and once the glue dries, then they've got a nice little card and a little keepsake. Yeah. So there we are now doing the meteor impact experiment. So that's, of course, in the upper photo, we see all the little plastic dinosaurs there. So actually, that's the surface of the Earth. It's the land before time, a time when dinosaurs roamed the Earth. And then I moved from talking about the great Cretaceous Tertiary impact 65 million years ago on our own Earth, and talk about the impact of impacts elsewhere in the solar system, including the moon. And that's what we're setting up down in the lower picture.
Where's Chuck?
Where's Chuck? Yeah.
Brian, just because
He's the dinosaur on the left.
Just in case it's not clear. In case it's not clear what's going on there, because I don't think Brian's giving himself enough credit for how clever this was. Those are trays filled with flour that it's got a little colored tempera paint mixed in, and he was having the kids drop marbles into the trays of flour, and that was producing impact craters, including the rays of ejecta and so on, and then they were able to look at that after and go and compare it to the moon, and so I thought it was brilliant, and the kids loved it. I thought that they'd be kicking the flour over and we'd be sneezing for weeks, but they behaved themselves and they really loved it.
Yeah, so. and actually one thing that you can do with this, that little disposable tablecloth I have on the floor, I purposely crinkle it up so that there's some ridges and dips in it. And when they do the impacts, you can see the ejecta. If you have different colored tempera paint in the various pans, we didn't get to that point where we actually had all the different colors in yet. But once all the different colors are in, and you have blue ejecta coming out one way, you've got red ejecta coming on top, you can actually see the relative order of the impacts because you can observe what color is overlying another, which is what planetary geologists do. That's one of the most important things they do, is determine the relative order of the events. Yeah, so once all that has happened, we take the pans away, and you can see what's been left over. Now it looks like real craters on the moon. You see the empty spaces where, we'll say where the craters are. You see all the ejecta rays, but where ejecta has flown out, and it might have been caught on a ridge, and there's actually a shadow on the other side where no ejecta landed, but it skipped across to over here. And I tell them that I can observe what's going on that mat, and they can observe what's going on that mat, and if they happen to see a ray on the moon that gets interrupted but then continues.
Yeah, I thought that was brilliant, and the kids loved it. They particularly liked the dinosaurs because they were able to wipe out the dinosaurs with the comet impact. So it was brilliant. Something changed every 2 or 3 minutes in the classroom session, and it held their attention. So well done for Brian. So meanwhile, back at the ranch, I was outside in the cold with the solar telescope, and the teacher had a teacher's assistant, and they were bringing students outside to us 3 or 4 at a time so that they didn't go running off into the trees and terrorizing the neighbors. And I was running a hydrogen alpha scope outside. Now, what I find when I'm showing kids, and for that matter many adults, but especially kids, the sun in hydrogen alpha, is they look in the eyepiece and they see a red circle and they don't realize what they're looking at. Like it looks like that's the field of view and it's red. It takes a while to make the connection that, no, what you're looking at is the disk of the sun, and the edge isn't the edge of the field of view, it's the disk of the sun. So what I always do with solar observing with kids is I have a photo handy, and I had that photo on 11 by 14 paper, laminated, and I can stand there and show them and say, this is what you're going to see. This is the edge of the sun, and I would turn the photo, because there's always at least one prominence, so I turned the photo, and there was a prominence that looked about like that, about up here in the eyepiece. So I would turn the photo so that prominence is in the same place that it is in the eyepiece, and then you can tell them what to look for. So we said, look for the orange peel crinklies, and then look for, this was up here, look for this gas jetting off into the space. And with that help to help them understand the context of what they were looking for, they were all able to see that prominence.
I thought that actually was quite brilliant because the kids, as they came back into the classroom, while the other ones were going to observe, I said, so did you see it okay? He said, yeah, it was just like the picture. You could see right away where these pieces are shooting out from the side of the sun. So it put a little help ahead of time, and it made it a perfect observing opportunity.
Yeah, I find that photo, I mean, I know it's cheating, but I find that's like taking a photo of a galaxy outside to appreciate the faint fezzy, but I think it really helps to show the kids what they're looking for. Otherwise, they're just seeing a red circle, and they don't get it. So that worked very well. So tips for doing this, of course, hydrogen alpha observing is a little bit, or solar observing is a little bit scary. So we have some rules to live by, and this is why there were two of us. Never leave a solar scope unattended, especially with kids around. We've heard stories of kids, oh, I think it would be really fun to tease my schoolyard buddy Jimmy by pulling the filter off while he's looking. Ha ha ha, won't that be funny? So we never, ever, ever leave solar scopes unattended, and the filter is always double fastened. In my case, it screws in, and then I also had masking tape at several places so I could see at a glance if it was working loose. And the other thing, we made a point of talking to them in the classroom, because what we didn't want is them thinking, oh, wait, was that ever cool, and going home and looking at the sun with their binoculars. So we made a point of talking to them in the classroom about the fact, and we kept it really simple and said, look, nothing you have in your life will make it safe to look at the sun. Anything you can think of isn't good enough. Nothing you have, unless you're an astronomer, will make it safe to look at the sun. Don't do this at home. And Brian made sure that he told them the sun was a big ball of gas, and we lied a little bit. We told them the crinkles where they were looking at was the waves in the gas and so on. We just keep the story simple enough for kids. So that worked fairly well.
What do you mean we lied? That must have been you lying.
No, it was him lying, so yes. And we got some feedback. So I guess our feedback is, boy, was that fun. Really enjoyed it. It was well worth the day off and the long drive to Shawville. I'd do it again. I think Brian used to do it all the time, so I don't know if he'd keep doing it again, but as I said, he did it in the cafeteria again afterwards too. And we've got a bunch of email feedback from the teachers. They liked it. The other teacher who were jealous, how did you get astronomers? Why didn't we get them? And she said, well, I asked. So she was feeling very smug. Apparently they're trading those meteorite cards like baseball cards. That was the teacher's phrase. So the kids had a ball. So you can do this. It didn't require much technical expertise. It just required a little bit of organization, 2 people, and the will to do it, and it was a lot of fun. So.
For those of you who are perhaps this is your first time here tonight and haven't followed the chain of how this has evolved, Tafa Music is an orchestral group that's based in Toronto, and they have been on tour for about 6 months, and they're going to continue to be on tour as well, delivering a project or a concert called the Galileo Project, the Music of the Spheres. Now, just going a little bit back in time, this was the Galileo Project was an idea that was conceived back in 1997 as an astronomy concert or to be an astronomy concert by John Percy. And eventually the idea evolved into a really polished program of astrophotos synchronized with music. And at the same time, they had a narrator who interjected at various points, reading the words of Galileo, reading the words of Kepler and Newton and so forth. And what made this concert unique, as I found out, is that the musicians memorized the words. I memorized the notes. It was all, there was no standing behind, displays reading their notes. It was all done off the top of their head, and that allowed them a certain amount of freedom to move around and so forth. So on to what we did. We were, this was a big surprise for me, and I know the Ottawa Chamber Music Society who we worked with, because we were expecting, they told me they'd expect 300, maybe 400 people. Well, they just, I got the final tally the other day, they got just under 1,100 people, just shy of 1,100 people that showed up at the event. And for us, that was quite apparent, because as I'll explain in a moment, that there was a lot more numbers people than we had originally thought there would be. Our center's involvement, what we had was we had a telescope. As Gary mentioned earlier, that we had his daub outside. So as patrons were entering the Dominion Chalmers United Church downtown, they'd walk in, and there was Gary's telescope, and it was looking at the Venus and the Moon, right? I think you said. And there was just a beautiful crescent that attracted a lot of attention. And we also were lucky enough to have a very big, long room, and we actually used up a good portion of this room with many different displays. Now, Ron St. Martin had his meteorite display. Tim Cole had his telescope set up with a projector and a screen. We had our main RASC display panel with lots of colorful photos that we've created recently and captions. A light pollution display, a moon display. Mike Lalonde was there as well, helping out, and he had his telescope set up with plenty of literature, and I had the table with all the IYA freebies and various handouts. So, as I said, we were really surprised by this because, as you can see in the photos, there were a lot of people that showed up, and in particular at intermission, there was an intermission, and people spilled into this room, and it was something to go from. It was a binary thing to something to go from. No one except us in the room, Ron and myself and Tim, and then all of a sudden have just a sea of people come in, and they came in all right. They surrounded the tables, several deep. Lots of questions that were coming at you at multiple directions, and one thing that I really find really encouraging, and I wanted to thank him again for doing this, is that Chris saw how busy we are, and sort of Chris came around the table and helped with his wife, and I really appreciate that, Chris, because it was we really had it was unbelievable how many people there were there. It was certainly quite a I don't know what word it is, commotion or whatever. We sold out all the RASC calendars. They're all gone now. And one of the things that we did, which really I didn't think much of it prior to the event, but we started to do this recently, is we have a sign-up sheet. When basically on the sheet we say, would you be interested in being notified about public stargazing events and other astronomy events in Ottawa? If so, leave us your name and your email. So this, I had four or five of these sheets. They all got filled, and this sheet was being pulled back and forth, and names were being added to this. And so I think this is wonderful. So these are people who are telling us that we want to come back. We want to be more involved. We want to be more involved with you in the future. So for me, that's a bit of a validation because, and I think maybe some of you might have been perhaps skeptical when you're talking about crossover event, particularly about these outreach events where you're crossing over into a community that's quite a bit different than ours. A concert-going community, astronomy club. Should we be reaching out to them when the interests are so, diverse, so different? I guess the validation was just from the so many names that we saw that we collected. People were saying we want more. Okay, so you can be sure that I'm going to be emailing them about future events and so forth. I think. Here's one thank you that we received from the Ottawa Chamber Music Society, and I think that says a lot about our group, and I'll let you read it. Okay. Okay, Chris. So I want to thank not just the people on the screen here, and I know the people on the screen here, they put a lot of work into making this night a success, but really all the people who've listened to my dumb ideas over time, and they've sort of fed back some ideas on how we can make these kinds of things better, because I think as we go forward, we're making them better and better and better. And I think that's what it's all about here. So I think we should really be, as I mentioned earlier, I do a lot of comparisons with other centers and so forth. We've come a long way. And I think we should all really be proud of what we managed to do with Talbot Music, because it was good. Thanks, everyone.
I was one of the people who were skeptical about whether or not a music and astronomy crossover event would work, and I am absolutely delighted to be proven wrong. The real thanks for making this work goes to Mike. Who made it happen. Who did some public solar astronomy at Penny's Point.
I'm not sure what you have for say next.
Okay, I think there's only 3 pictures there. Thanks, Attila. Yeah, I've never been to Penny's Point before to do any astronomy. I know that RASC has gone there many times before to observe in the evening. 2 weekends ago, May 1st on Sunday, Piney's Point had a family day where they had sleigh rides for kids, a lot of other outdoor activities, and we had the opportunity to go down and partake in those activities. So Mike Moghadam and myself went down there. We met with Sarah, who's the coordinator down there, and she allowed us to set up right beside the barn there. Mike had his table with an easel to show how we're going to be looking at the sun, and he had all of his International Year of Astronomy handouts, small little sundials for the kids, the little paper sundials that they can make. And basically we had the opportunity to visit with the parents and the kids as they came from the parking lot out toward their activities, and then sort of we caught them on the backslide, I guess, as you could say, as they finished, and had another chance to look at the sun. Like Richard said a little while ago, the sun it was pretty blank. It was essentially blank that day. There was no solar activity on the surface that you could tell. So what we did is I had two hydrogen alpha telescopes with me. I had a 60 millimeter Lunt hydrogen alpha telescope, and we were viewing the sun in full disk at about 50 magnification. It was good because you can see the orange peel effect of the granulation on the surface, and we were lucky enough to have a fairly large prominence that hung around all day long, or at least the whole time that we were there, that you could see quite easily even at 50 power. So typically what we do is we would have people look through the small telescope to get an orientation of the sun's disk. And in the larger telescope, there's a 6-inch refractor I have there with a solar spectrum filter, which is it also has a lot narrower bandpass than the Lunt telescope, and it had the opportunity to look at that same large prominence at about 200 power with a lot more resolution. So we had the opportunity to have a look at the disk of the sun, the full disk, and then an opportunity to look at the same prominence under a lot more magnification, which gave it a little bit more excitement there, and people enjoyed the views quite a bit. So young and old, I think that altogether we had about 60 people come by in the few hours that we were there. We only set up from about noon to 3 o'clock in the afternoon, but it was a beautiful day. It got a little bit windy and chilly near the end, but we were protected being right against the barn there, and it was a very enjoyable day for sure. Just some of the other slides here, I think there's basically the same scene, but yeah, it was a very enjoyable evening. We had a lot of fun. All right, thank you.
What Ken's been telling you is his hydrogen alpha astronomy gear is about as high end as you can get, so I suggest that you
Go observe with him. That's the opportunity you have simply to drool over the super fine gear. We have a couple of announcements. One of the interesting things about the International Year of Astronomy is they have this cornerstone project called the Galileoscope, which is an attempt to manufacture very cheap telescopes that have about the same capabilities as the telescopes Galileo used, so they can be given to kids so they can reproduce Galileo's observation. This telescope in large quantities can be had for on the order of $20. Now the center would like to buy a huge quantity of these things in the hopes of getting them to kids, but we have 3 problems. The problem is that last year we overspent our budget by a couple $1,000, and as you may have remembered from the business meeting we had last year, this stuff took up half of our $10,000 budget. So people point out that we have an opportunity here. We would like to ask members to help the Ottawa Centre convert postage into telescopes. Well, it's very simple. Just sign up for the electronic version and save us lots of money, which we'll then convert into giving telescopes to kids. Works for me. I would be much more, as a kid, way more interested in getting a telescope than a stand. Just another minor note, being a member of the RASC gives you access to cheap magazine subscription to either Sky and Tel or Astronomy. Barry Matthews is currently handling the subscriptions. He'd like a volunteer to take it over from him, so if you're either interested in getting a cheap subscription or would like to help Barry, come talk to me and I'll give you Barry's contact information. Now I get to tell you about all the cool stuff we get to do after the meeting. very first thing that will happen is we're going to move outside, and we'll have the book library and possibly the scope library available. Outside, we can have a conversation. If you want to ask questions of our speakers, if you want to tell our speakers they did a terrific job, now's the time. Dig up Brian. Brian has got samples of actually the moon. They're probably lunar meteorite fragments, I believe. Yes. He's right over there, waving his treasure in the air there. And we'll have refreshments as well. Shortly thereafter, some of us are going to go to Kelsey's, and if you'd like to hobnob with this unsavory crowd over alcohol, I believe they look better after 2 beers. Come join us at Kelsey's. On the 16th and 28th, the Global Night is a large program that encourages people to go out and observe in public and to do light pollution measurements. Now, this is an excellent idea because one of the problems I run into every time I do sidewalk astronomy is I set my telescope on the sidewalk, let anybody look through it, and the first thing passers-by ask me is like, is something special going on tonight? Or why are you doing this? And I don't have a reason other than, well, I don't have a life, so I thought I'd come here and show you my toys. Here's an official reason. So you want more information, Google Global Night, or even better, we've arranged a human interface for you. You can talk to Rob Dick after the meeting, who is Rob here in the back. He's waving. These are your interfaces to Global Night. On the 21st, I'm going to be inviting people over to my observatory to observe my 25 inches. It'll be a really great time to look for Hickson clusters. So you've got no excuse for saying you can't find San Gius Hickson cluster. There'll be an observing opportunity for doing a Messier marathon. Now, a Messier marathon is an attempt to observe all of these objects, all 110 of these showpiece objects in one night. It is a test of stamina because it takes all night, and a celebration of star hopping skills. But you'd think that any particular time you'd only be able to see half of them because the sun's going to be up for half the time if they're evenly distributed in the sky. Well, it turns out that they're not evenly distributed in the sky. There's a hole in the sky where there are no Messiers. And if you wait for the sun to get into that hole near the next new moon weekend, you have a chance to see all 110, but it's quite a challenge. Now, the next date that will happen is Saturday, March the 28th. And this is quite a test of star hopping skill and your ability to drink gallons of coffee. To make this more exciting, I'm going to hand out at the next meeting a prize April meeting for the person who's logged the most objects with the same aperture that Messier originally used, 50 millimeters. Now, if you want to get some more information about how to do a Messier marathon, Google the phrase star hopping Messier marathon, and you'll find a very nice webpage with charts that you can print out, which lists all of Messiers in the order you need to find them in, because you don't start with one, because then 74 is going to be a busy setting before you can see it. So to celebrate this event, I'm going to hand this hard copy out as a door prize to the remaining people who are clever enough to hang on to their tickets. All right, I'd like to remind people we do have a 60-inch telescope at a relatively dark sky site. You can attempt a partial Messier marathon here. I'm not sure if the horizons are good enough. If you want to go here, watch the RASC mem list, because Elsie will be posting conditions about the road. Occasionally it's icy, occasionally it's muddy. Sometimes the telescope requires repair, but most of the time it's in fine shape. And if you are going the route, please post that you're going, and perhaps people will want to join you. On April 2 to 5th is another major portion of the International Year of Astronomy celebrations called 100 Hours of Astronomy, which is an attempt to get people to literally do 100 hours of continuous astronomy. And the museum is going to have a small part of that. They're going to have a star party here in front of the museum with the Hohenheuer SOG telescope, the large dome in front of the museum, and telescopes from RASC volunteers. Mike Moghadam will shortly be circulating email requests for people to volunteer for this. And we're hoping to attract a reasonable number of the public. Those amongst you who are calendrically astute will recognize that this overlaps completely with our next meeting, which is at exactly the same time. This is a scheduling overlap that we have no control over. So what we're going to do is we're probably going to have an extra long intermission during the meeting so that people who are attending the meeting can have a chance to go out and have a look at Saturn. That's if it's clear. Now usually we end it right here, but there are a couple more events in the immediate following days, so we're going to give you advance warning now. On the very next day, on Saturday the 4th, Mike Moghadam is organizing a solar star party where I'm going to bring some hydrogen alpha equipment, and we're trying to talk. Ken ends up bringing his high-end equipment. And I'm probably going to do this at Pinecrest chapters or possibly Canada chapters as part of our contribution to the 100 Hours of Astronomy. And we figured we hope to get some kids looking through telescopes here because as Rich and Brian have pointed out, it's pretty tough to get young kids to look through a telescope at night. Also, this comes to us from Richard Andreevich, who has a, and the Glengarry Stargazers. They were arranged for a talk in Cornwall at the Best Western Hotel from the real-time support manager of the Canada Space Arm, Tara Hildebrandt. This is a free talk, and they're even going to feed us, or at least give us refreshments.
There's a handout for that on the stage.
Yes, there's a handout right here. If you'd like to take the details home with you. And wait a minute, the meeting's not over yet. Remember, there's still that astronomical dessert that I alluded to. But at this point, I'd like to thank the audience for attending. There were 118 of you composed of normal matter, and one person in a state of quantum uncertainty. I think that must have been Brian. I personally would like to thank Chris Terran in the pilot's position for running the show, and Tim Cole in mission control at the back.
Actually, Pam Wolf.
Pam Wolf too?
No, I was just sitting in. She was doing the work.
Okay. Pam Wolf and Richard McDonald for supporting your deals, and all of the many presenters and people who submitted observing reports. And thank you for attending. Did you guys have a good time? All right, if you did, come complain to me in private. All right, the Astronomical Eye Candy. This is a little film documenting the life cycle of a star. It runs in mere 6 billion light years, but for those people who need to go to bathroom breaks more often than that, we speeded it up for you by a factor of 500 trillion. This runs about 6 minutes. Ladies and gentlemen, that is the meeting. Thank you very much.